We're going to talk about a few real-world analytics applications that I personally have been involved in. The first application area that I want to talk about is in healthcare and medicine. The reason being is that I have been in this domain for quite some time, applying different analytics applications to complex healthcare problems and complex medical situations. Idea here is not to replace the traditional medical and research practice, but help them, augment them with evidence, with actionable insights so that they can do better at what they do. Idea is to discover a new pattern, new correlation, so that this medical and biological research can shift their direction towards things that have not been tried before, and by doing so, potentially leading to a cure for a chronic disease. Those are the kind of things that you're shooting for when you're applying analytics in healthcare and medicine. As we mentioned before, there is so much that can be done in healthcare and medicine. The cost is high, the outcomes are not justified. So we need to streamline the system to the extent that possible to make it less costly, better diagnostic, better treatment by using evidence-based medicine, looking at what has happened, extracting the knowledge, turning them into business rules, and applying them and putting them in place in medical settings. I have had projects that deals with cancer data. I studied breast cancer data, published several papers on it. We also studied with my research group organ transplantation process. How can we make things better, more efficient in that process so that more people can be matched with the proper organs for survival purposes. And we applied analytics, both predictive and prescriptive, on organ transplantation process in the United States using 10 years of data. And then we figured out that as opposed to using a opinion-based match mechanism that determines who should get what organ, instead, if we were to use evidence-based data mining, algorithmic-based match algorithm, the survival rate of certain organs could be increased by 10 to 15%. And again, there are some literature on it. If you're interested, you can dig it up and take a look at it. So the motivation in healthcare and medicine is that there are large data sets readily available. Government has nonprofit organizations sponsored by the taxpayers' money to collect and make those data sets available to research institutions to advance the healthcare and medical area. Data is usually in a good shape, organized, mostly complete compared to the data that you would see in other practices. The literature is rich and fairly organized, so the terminology taxonomy is in place for you to better understand how different components in healthcare and medicine kind of relate to one another, so that you can aggregate the information at the taxonomical level. And it is for a good cause. If you end up discovering a pattern, a correlation that leads to cure of, say, cancer, you would serve the purpose of your life. That would be awesome. Those are the motivating factors that makes healthcare and medicine a very good area for analytics applications. Another area where I spend quite a bit of time is in the area of entertainment and sports analytics. On the entertainment, since 2001, with a colleague of mine, Ramesh Chadha from Oklahoma State, we have been building these predictive models to assess and forecast box office success of Hollywood movies. In our models, we use everything before the production of the movie started, all the characteristics about the movie, and then see what success category it would fall into. And to be able to do that, we use historical data. Basically, every single movie produced in Hollywood. We characterize the movies into different numerical and symbolic variables and then tie them to their financial success using past movies and create the models, prediction models, and apply those models to new movies and project their financial success. Once the movie is released and the numbers are apparent, then we compare the actuals to our predictions, and then we make adjustments to make the system as accurate as possible. So since 2001, we have included large number of variables, characteristics, including text mining, into the mix so that our models would predict as accurately as they possibly can be. To the best of our knowledge, our models predicts better than any other model published in the literature. So if you look it up, you will find quite a few papers that we wrote on this particular domain. It's a beautiful area because most people think you cannot judge the financial success of a movie unless the movie is launched and put into the theaters and the people starts talking about it either positively or negatively. But we argue otherwise. For decision aid, we need to know which movie is going to generate the profit before the movie is actually produced. So we're looking at it from the decision support standpoint. On the sports area, with a colleague of mine from University of South Carolina, we put together a system early in the beginning for March Madness. We wanted to predict the outcome of March Madness, the basketball, college basketball games for our own university polls and competitions, if you will. And then we leveraged our models to have a certain level of success in our respective schools. But then we took that knowledge that we built and applied it to NCAA bowl outcomes. The idea here is that at the end of the season, college football teams get to be matched to one another, the only successful ones, in equal strength. So what it makes is that it makes it even harder to predict which team is going to be the winner, which team is going to be the loser. So we spend quite a bit of time to formulate the problem and then collect the data on for each team's offense, defense, special team, their conference, their historical performance, their composition of freshmen, the sophomores, the seniors, all of that information, large quantities of variables, and as far back as we can go with the data set, with the bowl games, and then build the models. And we were significantly accurate in predicting the bowl outcomes compared to, say, some of the Las Vegas odds. And we actually did compete against the odds for the future season and showcase that our system actually predicted better. This particular paper was published on International Journal of Forecasting. For those of you who are interested in building analytics models, it would be a good thing to actually dig up this article, take a look at it, and figure out how we did what we did so that you can learn from it and do your own bowl predictions or any sports outcome predictions. In fact, we're going to use the data set that we used, a portion of it, to showcase some of the capabilities of the different data mining tools in this live lesson. So we're going to look at what data we actually used and what outcomes that we actually generated. Another interesting area where we applied analytics is the critical analysis of car crash data. Idea here is to figure out what are the things that leads to severity of injuries in car crashes. There are a ton of data collected and made available to research organizations, public data. I have all the links, and all those links are actually in the published papers in this particular domain that you can go to and download your own data and do your own analysis if you wanted to. Idea again here is to figure out what are the characteristics of the crashes that leads to severe injuries. Now, one might think that it would be weather conditions. If it's rainy, snowy, icy, it leads to worse outcomes. Mathematical algorithms says otherwise. They say, and they imply, not say, but imply that when the weather conditions get worse, drivers get a little more cautious, so the proportional outcome of the injury severity at bad conditions is not much different than the good conditions. What ended up being a significant contributor to severity of injury, not a surprise, seatbelt. Not airbag, not the size of the car, but seatbelt. Seatbelt significantly improves the outcomes of a head-on collision to car crashes, along with other variables that are all captured and represented in those research articles that you can dig up if you search it by crash analysis with my name. I'm not the only one. There are hundreds of other people who have actually used similar data sets to conclude in somewhat similar knowledge that this research actually produced. Another application area where I have been involved in for the last few years is in education. Idea was to figure out models that could pinpoint at-risk students. At-risk students are the ones who are most likely to drop out before they actually complete their degree. In a university setting, in a student success center, this is one of the key metrics that they are judged as far as their success level is concerned. What is your retention rate? What portion of your freshman students are showing up as your sophomore students? A lot of the schools has attrition rate between 15 to 25%. That means 1 out of 5 students in average is not showing up for the second year. What can we do about it? A lot of universities hire consultants, and consultants comes and does survey-based analysis, provides them with quote-unquote knowledge nuggets as to how they can improve their retention rates. But in the day of analytics, what we need to do, and that's what I'm proposing in this research, is to tap into what you already know about students and what you already know about their high school success, know about their personal characteristics, know about their social connectedness, know about their first semester performance, collectively link them to their possibility of returning for second year. So at the end of the first semester, you run the model, you identify at-risk students, you have 1 semester to do what you need to do to retain those students. And the models that we developed were significantly better predictors of at-risk students than the knowledge-based, heuristic, gut feeling-based algorithms that many universities are using nowadays. A lot of universities, including University of Alabama, several other universities, are moving towards this analytics-based student retention practices, using all the data captured in multiple databases from financial to educational to residency, collecting them and identifying the students and figuring out what factors leads to attrition and then augmenting and mitigating those factors to improve and increase their retention rates. Beautiful area. The same context actually applies to customer retention or employee retention. The phenomena is the same. The data set will change. The outcome will be models that predicts who are those customers that are more likely to leave your products and services and go with your competitors and why and what you can do about it. So contextually, if you look at it, they're the same.